This presentation will be the first of two that serve as recaps for all the lectures discussed from right after LE1 to before the suspension of classes. We hope that we can get you up to speed for the first summative problem set or SPS1. The coverage of SPS1 will be from lecture 19 covering magnetism to lesson 31 on RLC circuits, but it would be better if you check the coverage on your updated syllabus. Let's clarify some matters. First things first, this recap presentation is incomplete compared to the lecture slides we've used in lectures prior to ECQ. We should still send you the original lecture slides as a more comprehensive reference if we haven't done so already. Second, this covers magnetism, or lecture 19, to force and torque of current loops, or lecture 22. Another recap for lectures 23 to 26 will follow. So please make sure to pause or go back to this slide for reference to the contents of this recap. We begin with lecture 19, but we focus on magnetic forces. We'll lightly go through cross-product conventions with unit vectors, as I believe it's good that we review them, and a refresher on the right-hand rule, because we're going to use the right-hand rule a lot. Afterwards, we're going to solve a relatively simple problem. Due to the misaligned nature of velocity, magnetic field, and magnetic force vectors that we deal with in magnetism, cross products play a crucial role in expressing the phenomenon mathematically. To review our cross product algebra with Cartesian unit vectors I hat, j hat, and k hat, it's nice that we observe that it follows a cyclic permutation. For example, as you can see in the figure in the left, that those arrows point that I hat crossed with j hat is positive k hat, j hat crossed with k hat is positive I hat, and so on and so forth. So the first three permutations in the cycle, I hat cross j hat k hat, all the positive ones are on the top right side of the figure. Unlike dot products though, factors in cross products do not commute. This implies that the placement of these factors do matter. As an example, if we reverse the direction of the cycle, we resolve negative unit vectors. J hat crossed with I hat, as you can see it goes against the flow. If you go against the flow, you get a negative k hat. And this follows if you try to go against the cycle here, that you get k hat cross j hat is equal to negative I hat, and I hat cross k hat is equal to negative j hat. At some point, it becomes second nature to you, so I wouldn't really worry about having to memorize all of this. The right-hand rule provides visual or kinesthetic assistance in keeping track of how the vectors are supposed to be ordered in cross products. You may wish to pause or go back to this slide as a review to read the complete details, but I'll give a quick rundown. Let's consider the cross product of velocity with the magnetic field, or V cross B. Using our right hand with the palm open, point your finger towards the direction of the first vector, or V. Proceed to form a thumbs up by curling your fingers towards the direction of the second vector, or B. Your thumb should then point to the direction of the product vector. If you find yourself contorting your whole hand just to be able to complete this process correctly, it may help to flip the direction at which your palm is facing at the start. Since cross products are used mostly to describe quantities dealing with charged particles in magnetism, we must be conscious if the charge of the particle of interest is positive or negative. For negative particles such as electrons, the correct direction is usually the opposite of where your right thumb points. This is why some people prefer using the left-hand rule when dealing with negatively charged particles, but at the end of the day, it's up to you. So let's try solving our first problem. A proton, at the origin, moves at a velocity of 30,000 meters per second through a uniform magnetic field of 2 Tesla directed along the positive z-axis. The proton moves on the xz plane and is angled 30 degrees from the positive axis. We are tasked to find the magnetic force that the proton experiences, or F sub b. We begin the solution with F sub b equals qv cross b. In solving problems dealing with magnitude, direction, and whether we're dealing with negative or positive charges, it helps to confirm the directions of vectors first, before calculating the magnitude of the force or the field in future calculations. You can do this by having a quick glance at the figure. After that, you can just check whether the charges that you're dealing with are positive or negative. Now, since the particle of interest is positively charged, q greater than 0, we can use the right-hand rule directly to know that the magnetic force should point in the negative y direction, or negative j hat. We can then solve for the magnitude with the equation FB equals QVB sine theta, or sine phi. In this case, our angle between V and B is 30 degrees, and that gives us an answer of negative 4.8 times 10 raised to the negative 14 newtons, J hat. Now, we added the negative sign here because that's where our vector is supposed to be directed. Do take note that some problems may give negative charges instead of positive ones. Also consider how the principle of superposition can help solve problems or solve systems with multiple charges. Moving on to lecture 20, we pass by magnetic field lines, magnetic flux or phi sub b, and the motion of charged particles or cyclotron motion. A more detailed discussion on the convention of magnetic field lines is in lecture 20. For now, it is enough for us to discuss the highlights. Firstly, the direction at each field point is unique. It follows that magnetic field lines should never intersect. At any field point, there should only be one direction at which the particles are influenced to go to. While these two properties are shared by both magnetic fields and electric fields, the third one is unique to magnetic fields. Now, unlike electric fields, magnetic field lines have no starting or ending point, or we call them sources and sinks. The magnetic field lines always traverse in closed loops, as you can see on the figure on the right. Now, it may seem tricky that these lines are broken, but that's because it's just limited to the size of the picture. I can assure you that those lines will eventually be connected by some larger loop that goes beyond the borders of the picture. Because the moment that the magnetic field lines actually have a start and end point, we have a breakthrough. Similar to electric fields, magnetic fields can be quantified by how much of its field lines pass through surfaces, or magnetic flux. Now in general, magnetic flux is calculated as the integral of the dot product of the magnetic field to an infinitesimal area element dA. If the angle phi between the area and the field vector is known, then the integrand may be re-expressed with a cosine factor. Now, for magnetic fields traversing through any closed surface, the total magnetic flux will always be equal to zero. And that's a fact. The result agrees with the previous assertion that magnetic field lines do not have sources or sinks. The lack of ends of magnetic field lines admits that whatever line enters a closed surface is bound to leave it at some point. Lecture 20 also discusses the motion of charged particles. Specifically, cyclotron motion is the movement of charged particles in uniform circular motion when it is immersed in constant magnetic fields. So consider the figure on the right. A proton, traveling with some velocity v, is immersed in a constant magnetic field B that's pointing into the page. Now, with the right-hand rule, you can check that at any position where the proton is placed, the magnetic force will always point radially inwards towards some center of a trajectory, a circular trajectory. This suggests that the magnetic force is the force that actually provides centripetal acceleration and consequently driving uniform circular motion. The left-hand side of the equation is just QVB because V is always perpendicular to B at all points in its trajectory, and the right-hand side is your familiar mv squared over r from mechanics. The radius of the trajectory has a special name called the cyclotron radius, and you can calculate it by isolating r from the previous equation, which should give you its expression. The cyclotron frequency f may be calculated using the angular velocity. Now, noting that omega is equal to v over r from your rotational dynamics, f is given to be qb over 2 pi m. Now, another common quantity is the period, which can be calculated from the simple speed equation. And noting that the distance traversed is just the circumference of the circle, and after a few steps in algebra, actually just one step, we have t being equal to 2 pi m over the absolute value of q times b. Now, it is also the inverse of f, as you can check, and also as expected. Let's try solving a problem involving cyclotron motion. An electron at point A has a speed of 1.41 times 10 raised to the 6 meters per second. And then we first look for the magnitude and direction of the magnetic field that will drive this specific electron to traverse this path. The path is from A to B, and take note that the trajectory runs clockwise. It is stated in the figure, or you can imply from the figure, that the radius is 5 centimeters. Since the electron undergoes uniform circular motion, the magnetic force should point radially inward. Now usually when we perform the right-hand rule, it's the force that we're looking for, not the second factor in the cross product, in this case B. So there is a workaround for this by opening your palm and pointing your thumb towards the force, so to the right, and the rest of your fingers towards velocity, which is up. The direction at which your fingers curl when you close your palm should point you to the direction of the magnetic field if the particle were positively charged. But then we have to note that in this case we're dealing with an electron. So if you just do it blindly, you point your thumb in the orange vector, you point your other fingers in the green vector, you're going to curl towards you or out of the page. But since you have an electron there with you, you're supposed to reverse the result. And in which case, you'll end up with a B that is pointing into the page. Now, alternately, you could use the left-hand rule. Using your left finger or left hand, you point your thumb still in the orange vector, you point your other fingers in the green vector, and then you curl your fingers. And you notice that your left hand will curl into the page. So it's really up to you what kind of technique you'll use when you end up having to deal with a negative charge. The magnitude is then solved or you can solve it by applying the formula for the cyclotron radius, and all you have to do is isolate B. The magnitude of the magnetic field is then B equals 1.60 times 10 raised to the negative 4 Tesla. We then look for the time required for the electron to move from A to B. We simply use the formula for the cyclotron period, but with a slight modification. For a full circle, well, the formula is posted from slide 13, or it's just T equals 2 pi m over absolute value of Q times B. But then, since the path of interest is a semicircle, we just take half of that result. And that answer should just be T equals pi m over Q times B, or 1.12 times 10 raised to the negative 7 seconds. Now let's go to the last two lectures for this recap. We explore forces and torques of current carrying loops and wires. Part of the lesson introduces the concept of a magnetic moment, or mu. Now, a quick summary should suffice for these two topics. An important distinction we have to make for these examples is the fact that we are not dealing with discrete point charges anymore. We turn our attention to a continuous collection of charges moving along conductors continuously, and this can aptly be described by currents. The magnetic force produced by a straight wire is just equal to, well, FB equals IL cross B, where I is the current, but then since I is not a vector, we vectorize the length, being L, so the length of the wire being L, pointing in the direction of the current flow. The magnitude of this force may be expressed in terms of the sine of the angle between L and B, so it's usually phi. Infinitesimal wire segments become useful when dealing with arbitrarily shaped wires, which we see more of in the magnetic field calculations eventually. The magnetic force contributed by an infinitesimal wire segment of length dl is just equal to IDL cross B. Moving on to the last lecture for this recap, we focus on current carrying wires formed into closed loops. Now, an interesting property of these current loops is that when immersed to constant magnetic fields, the net force experienced by the loop is actually zero, but then the torque is non-zero. Then we have this magnetic moment mu being a property of these loops to experience a mechanical moment under the influence of magnetic fields. I took the liberty to show the general expression as the product of the current I running through it, its area vector A, and the number of loops that are formed, N. The direction of mu may be determined with a modified right-hand rule. You curl your fingers along the flow of I, and your thumb should point in the direction of the vector of the magnetic moment. Now, the torque experienced by the loop is the cross product of mu and B, and the potential energy is the negative of their dot product. More details on these, particularly with the stability of these moments, may be found in the lecture slides. So this is very similar to the electric dipole moments and their stabilities from LE1. So that's it for this recap. Thank you for listening, and I hope that you listen to the next recap.